Hello, and a big welcome back to all my subscribers. And if you're not a subscriber, why not? What's wrong with you? So I'm going to carry on with the series on teaching people how to do RISC-V assembly language programming. In this section, I'm going to talk about installing the GNU Toolchain on the virtual machine, the Linux and Ubuntu virtual machine. Now, if you haven't watched that video, I'll put a link up here somewhere to a card that will take you to how to install the virtual machine using QEMU. Now, installing QEMU, well, I'm going to leave that as an exercise for yourself. But one thing I did want to mention, which isn't in the video, let me just show you that now. When you use this virtual machine, it is often very difficult to use the character display. So when you're using Vim or Emacs or whatever, it doesn't display properly in the terminal. So what I've done to get around that is I've used this command here, netdev user id net0 host forward TCP/IP and then a port and then 22. And what this is doing is the guest has the OpenSSH server running on it on port 22, which is the normal SSH port, but that's being redirected on the host machine to 5555. So that allows me to SSH on port 55 and it goes into the virtual machine. And that means that I can use the virtual machine and I don't have any problems with the actual the usage of the Emacs or Vim or whatever. All the characters line up and everything works because it uses the term cap from the SSH. Anyway, so once you've installed the software, then the next bit is you need the tool chain. You need things to work properly. So what we'll do is, sorry, just get that ready. Let me just walk you through what we're going to do here. So before we dive into the installation and the usage of the tool chain, it's essential to understand the components that are involved in transforming your source code into an executable program. So these components include the compiler, the assembler, the linker, and the concept of object files. So a compiler takes a high-level source code written language like C or C++ and turns it into assembly specific for the architecture, in this case RISC-V. And the GCC compiler collection provides compilers for various programming language. For RISC-V, there's a RISC Linux GCC command, which you can compile C code and target the RISC assembly architecture. The assembler takes the assembly code and converts it into machine code in a format known as an object file. Not an executable. It uses object files. Object files contain a combination of machine instructions, data, and information needed to place the instructions correctly in the correct order in memory. So it has symbols and relocation information. So for RISC-V, the assembly step is typically handled internally by GCC when compiling high-level code, but can be invoked separately if you're working with assembly language like we will be. Now, the linker plays a crucial role, and it's the final step in the creating of an executable program because it takes one or more object files that are produced by the assembler and combines them into a single executable file. So in order to do this, it resolves references to undefined symbols by finding the correct address of the functions and the variables inside the other object files or the libraries, and it links them together. So the linker arranges the sections of the executable, like the code and the data segments, and it handles the inclusion of any required library code. Now, object files are binary files, and they're produced by the assembler during the compilation process, and they contain machine code or binary instructions that the CPU can execute, but it can't execute it in the form of an object file directly in an operating system. The object files have metadata like symbol tables and relocation information. So an object file is there to help the linker combine multiple object files into a runnable program. Now, typically object files have an extension of .o in Unix-like system. So you may have seen some before. So the process of source code to executable is the compilation is the first step. The source code in a high-level language is compiled into assembly language for the target architecture. The assembly language is then converted into machine code, which is stored into object files. And the linker combines all of the relevant object files and libraries, if necessary, into a single executable program, and it resolves any references between the various object files and libraries and things. So the process is abstracted when using the toolchain with high-level languages like GCC can compile, assemble, and link the code in a single command. However, these steps are all crucial for debugging and optimizing build processes and working with the assembly language directly. Now, I'm going to guide you through the installation of the RISC-V GCC toolchain on the Linux machine, and as I said, if you should have it on the virtual machine. We'll verify the installation, and we'll look at how to install additional links like development manual pages, etc. Because understanding the toolchain is crucial for your assembly language programming, and it includes all of the compilers, assemblers, linkers, and debuggers, etc. that you're going to need when you're developing these applications. So by the end of this, you should be able to install the GCC toolchain on the Linux machine, verify the installation, install the development man pages for additional support. So let's start looking at that now. And let me just change this so that you can see what's happening here. Now, the very first thing we're going to need to do is we are going to need to update our system, right? And so, that's a bit better. We're going to need to update our system. Now, to update the system, it's relatively straightforward. All we need to do is do sudo update and upgrade like this. I'm not going to run the command myself because it'll just take too long. But basically you just do an update and upgrade to make sure that your system is up to date as much as it can be before you run this command, which is app install build essentials. Now, build essential has all of the things that you're going to need in it. It includes the compiler and the assembler and the linker, many of the man pages. It includes make, which we'll talk about later. And so once you've run this, you should have everything you need. Now, alternatively, you could install this from source, but I don't recommend it. It's going to take too long, and there's just too many things that can go wrong. If you're using the virtual machine that I suggested, then you will have Build Essential available to you, so please do that. Now, to verify the installation, once this is run, you can do gcc -- version, and it will tell you the version of the software, or at least show up. So this is all we need to know that it works. Now, what we can do is we can create a simple C program, which is basically just hello world. And we can compile this by doing gcc simple C, and output as hello world, I guess. So we should now have hello world running on the machine. So we have the linker, we have the compiler, so everything was done to make that happen. We would have had GCC, we will have had AS, which is the assembler, and we will have had LD, which is the linker. And we can do version on all of this just to make sure that we have these installed, which we do. So we've basically verified the installation of what we need. Now, the other thing we want to add here, and this is optional but useful, is install manpages-dev and mandb. Now, I'm not going to do that because it's already installed for me, but it will let you install the development pages. Now, I'm sure if you're into Linux, then you're used to man pages, you know, so you just type man and then bash or something, and it'll tell you how to use the bash page. But what we want is we do something like man to write. We're going to get the development page for the write descriptor. And so it's going to show you things like which libraries to include. It shows you the byte counts, seekable file, etc., etc. So these pages are for software developers. Now, one man page that I do want to show you is man syscall. Now, the reason I want to show you this is that a syscall is typically a system call whose assembly language interface. So you give a number and then you call syscall and it invokes that. Now, syscall is typically used on x64 or Intel processors, those sorts of things. But on a RISC machine, you need to call it differently. But if you look at the syscall, there's a table, if we scroll down a bit, which, let me just change so you can see the whole of the table. So you can see here on x86 the system call and the return value and things, but it uses syscall. But you can see on a RISC processor it uses something called ecall. So if you're using a RISC processor, you need ecall. If you're using one of these other processors, then it uses something different, like ARM uses SWI. So you need to be aware of these things if you're going to run system calls in assembler. But for us, our purposes, ecall is our go-to. And if we scroll even further down, it'll show you the arguments. So if you're used to x86, these are the registers it uses, but for our purposes we only care about RISC-V, and the processors it uses for the first argument is you put the first argument into the A0 register, and then the second argument into A1, A2, A3, etc., up to argument 6. So you can have up to 6 arguments when you make the system call. An example of this would be, for example, printf. So if you're going to print something, you would put the number of the call that you want to make in A0, and you would put the string that you want to print, or a pointer to the string you want to print, in A1. So, and that's how you would do that. So that is how you use your man pages for using to get information. Now, the next thing I want to basically cover is make. Now, the make file system is a really, really useful thing, whether you program in C or assembler or whatever. So what is make? Well, make is a build tool that automatically builds executable programs and libraries from source code by reading the file, reads a file called a make file, which the make file specifies how to derive the target program. So it determines which pieces of the programs need to be compiled or recompiled, and it issues the correct commands to recompile them. So the tool isn't limited to compiling programs. It can be used for any task where the file must be updated automatically based on changes to another file. So why do we use it in compilation? Well, the first is it's efficient, because without make, you would have to manually compile every source code file into an object file and then link all of the object files into an executable. So this is a time-consuming and error-prone process, especially for large projects, and make automates this whole process and ensures that all of the necessary files are compiled, and it saves time. But it also does dependency management. So make files excel at dependency management between files. So if a source file is modified, make knows how to recompile it and any other files which depend on it, but it won't recompile unchanged files, and therefore it optimizes the build processes. A make file allows the developer to define custom build rules, compile options, and relationships, custom relationships between source files and object files and executable files. And this customization makes it adaptable for many, many projects, from simple to complex applications. And it basically it automates repetitive tasks. So besides compilation, make can automate running tests, cleaning directories, removing old object files and executables, generate documentation, and it basically making the development process smoother and more efficient. And make usually can be used on different platforms, so like it's cross-compatible, so you can use it on Linux or Mac OS or Windows, and it supports projects in virtually any programming language, providing you have the appropriate compiler and tool chain available. And so this versatility makes it a valuable tool for platform development. So a make file, the central component of a make is a make file, and that contains all the directives for compiling a file. So these directives include the targets, the prerequisites, and the commands. So the target is usually the name. Let me just show you an example from one of my other videos. If I change to my convert, and I have a make file here. So the make file has targets, prerequisites, and commands. So the target in this example is this executable. So it's all of the steps required to get to this target. Now, prerequisites are files that have to exist in order for the target to be completed. So in order to create the target, I need object files. And to get object files, which are these .os, then I need to compile all of the assembly plus, in this example, a header file. But we need to have compiled with the assembler all of the assembly code files and the header into object files, and then it can take the object files and create a target. And so when it says target and prerequisites, this is what it's talking about. And then commands are the actions that will be taken by make in order to create the prerequisite or the target. So here it is basically saying CC is GCC, so link all of these object files. to create this target. Here it's telling it to use the assembler to assemble all of these into a object file. Now, make has some funky looking shortcuts basically to say every file with this name, or this is the output, or whatever. We'll go into that later, but just know that this is a make file. And in fact, it's a fairly simple and straightforward make file. So when you run a make file in a terminal, it reads the make file in the current directory to determine what needs to be built and how to build it. So here it knows that everything has already been made, and so there is no reason for it to do anything. But if I show you the make file again, remember I said you could have other commands that weren't just to build. In this example, it's clean. So I can clean out I can remove the target and I can remove the object files, and it just gets rid of all of this stuff. So now if I type make, it builds everything because there is no object file there. There is no executable, so there's no target, there's no object files. It knows it needs to rebuild everything, and so it does. And so it's rebuilt everything there. So if you consider this project, which had multiple source files, instead of compiling each one individually and linking them, this make file specifies how each object file is compiled from its corresponding source file and object file, and it compiles it and then links it and into a final executable. So running make handles the entire process and automatically recompiles, and it recompiles just the files that you need. So in summary, make is a very powerful tool for automating the compilation and build process, and it significantly reduces the amount of manual work and minimizes the number of mistakes, and it streamlines the development flow. And its ability to manage complex dependencies and customize the build processes. It just makes it indispensable in a modern software development project. And we are going to use make files in our program, in this scenario. So that is it for today. I am going to carry on and continue this later. We will be looking at next actually doing some assembly language programming, and we'll introduce things like the stack and the registers and system calls, or e-calls in our case. And then we're going to look at how to call libraries so that we can do things like printf, and basically build up the knowledge of doing assembly. Now, I did recommend in the last video a book by Robert Winkler, and if you get an opportunity, have a look at that. It's free, it's open source, so you can read it and you can look at it and you can check it out and you can play around and get a really good idea of what's happening. But in this set of videos, I'm just trying to get you to the point where you can then kick off and start to learn more yourself. So this is just really basic stuff, but once you know this, then you can build up your own knowledge using books like the one provided for RISC-V, or online information, etc., tutorials, all that good stuff. So this is just effectively a starter for 10. If you like these sort of videos, please like and subscribe and press the bell and all that YouTube jazz, because it encourages me to carry on. So thank you very much for watching, and have a nice day.